In this video, we are going to talk about reasoning LLMs, one of the biggest topics in AI right now. Since its release in September 2024, OpenAI's R1 generated many discussions, with some claiming it marked a fundamental shift in AI reasoning. Yet, within just a few months, we saw multiple teams like Google with Gemini Thinking, DeepSeek with R1, and now even xAI with Grok 3, we've seen all of them release their own reasoning models, showing that maybe this wasn't some unattainable breakthrough. So, what's really going on here? In reality, we'll see how reasoning models are an iteration on existing technology. They build on top of the GPT architecture and the transformer design we've already seen and discussed before. Like other LLMs, they still predict tokens one at a time, generating responses in an auto-regressive way. What sets them apart is their training. They are specifically optimized to produce reasoning chains for certain types of problems. Now, if you follow my channel, you know that I don't chase the hype. When OpenAI's R1 dropped, many rushed to make videos filled with speculations and perhaps exaggerated claims. Instead, I waited. I wanted to see how long it would take different teams to develop similar models. And of course, I also wanted some technical details, possibly some papers describing training methods and architectures, as it happened a few weeks ago with DeepSeek. My goal with this channel has always been to connect the dots and give you a clear reference map of a full topic, rather than just pushing out quick demos when a new model drops. That's why this video took some time to make. Before we start, a shout out to Sebastian Rashka, one of the main people I follow to understand deep learning and LLMs. I've based most of this video on one of his recent articles titled Understanding Reasoning LLMs that he published on his Ahead of AI mailing list, which I highly recommend you subscribe to. So, what are reasoning models for? Let's start with a comparison. If you ask an LLM what's the classic recipe for tiramisu, it can easily pull up the facts. Coffee-soaked ladyfingers, mascarpone cream, eggs, and cocoa powder. No reasoning required. However, take a problem like this. A pilot is preparing to descend for landing. Given that the plane is currently cruising at 35,000 feet and needs to descend to 3,000 feet at a steady rate of 1,800 feet per minute, when should the descent begin? Here, the model needs to calculate each step logically to reach the correct answer. A form of reasoning is therefore required. And that's where reasoning models like R1 and DeepSeek R1 enter the picture. They are LLMs just like ChatGPT, Llama, and Gemini, but they are optimized for tasks requiring structured, multi-step thinking, a concept known as chain of thought, where models are prompted to think step by step to reach a solution. In his article, Sebastian Rashka breaks down the ways to build reasoning models into 4 distinct approaches: inference-time scaling, pure reinforcement learning, supervised fine-tuning with reinforcement learning, and distillation. Now, we've seen elements of these approaches in previous episodes, especially around GPT models and reinforcement learning from human feedback. What we'll do now, we'll break down these 4 approaches in detail. Inference-time scaling simply means improving an LLM's performance at inference without changing its architecture or retraining it. Instead, it makes the model spend more computation time generating responses. The most common approach is chain-of-thought prompting, where instructing the model with phrases like "think step by step" helps it logically break down problems and improve accuracy on complex tasks. Chain-of-thought prompting is widely used to improve LLM performance on benchmarks like math and GSM-8K. Another approach under inference-time scaling is having the model generate multiple answers and selecting the best one using techniques like majority voting or beam search. In majority voting, the model produces several responses, and the most frequent or consensus answer is chosen. Beam search works by maintaining multiple candidate sequences and iteratively selecting the most promising one until a final output is determined. Ultimately, inference-time scaling means using more computation power during inference to improve performance on complex problems, and this can be applied to any LLM and does not require any further training. Following Sebastian's article, we'll now look at how we can improve on chain-of-thought prompting by training LLMs specifically for reasoning purposes using pure reinforcement learning. The idea is to train LLMs to generate more structured and effective reasoning chain of thoughts than would be possible to obtain with just prompt engineering. That's essentially what reasoning models are: standard LLMs trained to produce stronger reasoning chains through targeted reinforcement learning and fine-tuning. To understand how teams like DeepSeek built these models, we first need to review the 3 key stages in the standard training pipeline of an LLM. During pre-training, the foundation model is trained on massive datasets to learn both the structure of language and factual knowledge through next word prediction. This process allows the model to develop a broader understanding of language patterns, general world knowledge, and common problem-solving structures. During supervised fine-tuning, the model is fine-tuned on a curated dataset of tasks, instructions, and example responses. This step teaches the model how to better follow instructions and engage in conversational workflows with users. In reinforcement learning from human feedback, the model is prompted with various tasks, generating responses that are then evaluated and assigned a reward score. Unlike supervised fine-tuning, which uses a dataset of prompts and responses, reinforcement learning relies on dynamic feedback to refine the model. Rewards often come from human feedback, modeled through some scoring system that ranks outputs based on preference. Algorithms like proximal policy optimization adjust the model's weights to increase the likelihood of generating higher scoring responses. So, what happened with DeepSeek then? In the process of making their R1 reasoning model, DeepSeek's research team explored an idea. What if we skip the supervised fine-tuning step entirely and build a reasoning model using only reinforcement learning? Their experiment with DeepSeek R1 explored exactly this idea. They took their pre-trained foundation model, DeepSeek V3, a 671 billion parameter model, and skipped supervised fine-tuning altogether. During reinforcement learning, they prompted the model to produce explicit reasoning chains within think tags and its answers within answer tags. This structured format pushed the model to clearly distinguish between reasoning and final answers, and it facilitated the emergence of some reasoning behaviors when they applied the reinforcement learning process. But for reinforcement learning, we still need a reward system to score the model's answers, so that we can adjust the model's weights towards the higher performing answers. Here, instead of using a human feedback model as it's commonly done, DeepSeek developed a system of rule-based rewards to evaluate the correctness of an answer. This meant selecting only prompts with verifiable answer, such as math problems where the correct result can be checked automatically, or coding tasks where the output can be compiled and tested. In practice, they had two rewards: an accuracy reward, and these were assigned based on whether the generated code compiled successfully or whether a math problem was solved correctly, and format rewards, essentially evaluating whether the model's responses adhered to the desired format, including placing reasoning steps inside those designated think tags. To update the weights of the model during training, they used Group Relative Policy Optimization (GRPO) instead of PPO or DPO, which are more commonly used with reinforcement learning from human feedback. We won't go into the details of GRPO here, but if you subscribe to the channel, I'm planning an entire video on reinforcement learning. What we'll say here is that GRPO makes the training process more efficient and cost-effective. DeepSeek's R1 experiment was successful, demonstrating that the model learned to generate intermediate reasoning steps despite not being explicitly trained on a dataset containing chains of thought. This highlights that reinforcement learning alone can drive the emergence of reasoning patterns. Looking at benchmarks, DeepSeek R1 achieved a significant performance on the AIME 2024 test, a math competition benchmark designed to evaluate complex problem-solving abilities. The model's score jumped from just 15.6% at the start of reinforcement learning to 71%. When majority voting was applied, that is, when multiple answers were generated and aggregated for consensus, the score further increased to 86.7%, putting it on par with models like O1. So far, we've explored inference-time scaling and pure reinforcement learning. Now let's move to the next iteration, combining supervised fine-tuning with reinforcement learning. The DeepSeek R1 experiment proved that pure reinforcement learning could develop reasoning capabilities without supervised fine-tuning. However, it had notable drawbacks. Responses were often difficult to read, and the model frequently mixed languages, such as combining Chinese and English within a single output. These issues highlighted the limitations of solely relying on reinforcement learning without any supervised fine-tuning to guide the model. To fix this, DeepSeek reintroduced supervised fine-tuning into the pipeline, using what they called a cold start dataset to fine-tune their V3 foundation model. This cold start dataset essentially included cleaned up chain of thoughts from their R1 model. The aim of this cold start supervised fine-tuning was to condition the model to produce more structured and reliable outputs while addressing issues such as language mixing and unclear responses. After this supervised fine-tuning stage, they ran a first reinforcement learning step. They kept the accuracy and format rewards from the R1 but also introduced a consistency reward to reduce language mixing and enforce clearer responses. But they didn't stop there. To create a more general-purpose reasoning model, DeepSeek conducted an additional supervised fine-tuning stage, this time using a much larger dataset. This contained 600,000 reasoning examples, that is, prompts with chains of thought in their responses. This reasoning dataset was curated through rejection sampling, a method where multiple responses were generated for each prompt and only the highest quality outputs were selected, essentially filtering out mixed language responses, poorly formatted reasoning steps, and unstructured outputs. They also added a dataset containing 200,000 non-reasoning samples, essentially tasks like writing, factual question and answer, translation, and so on. These non-reasoning examples mostly came from the dataset they used to train their previous DeepSeek V3 model and is similar to what is commonly used in the supervised fine-tuning stage of general-purpose LLMs. The idea with this extended dataset was to allow the model to generalize beyond just structured reasoning tasks. After this second supervised fine-tuning stage, they finished with another final round of reinforcement learning, where DeepSeek combined multiple reinforcement strategies to enhance both reasoning performance and alignment with human preferences. For reasoning tasks such as math and coding, they continued using rule-based rewards, the same they use for DeepSeek R1. For more general question answering and alignment, they used a human preference reward model, essentially what's commonly used for general purpose LLMs during reinforcement learning from human feedback. This final reinforcement learning phase helped refine DeepSeek R1, improving its reliability and effectiveness across a broader range of tasks. Benchmarks reflect these gains. For example, DeepSeek R1 achieved 79.8% on the AIME 2024 math competition benchmark, along with 97.3% on the Math 500 benchmark. In coding, it reached a 2029 ELO rating on Codeforces, placing it above 96.3% of human participants. Beyond math and coding, DeepSeek R1 also demonstrated strong performance in general-purpose benchmarks. While this training process involved many steps, the core ideas remain simple. Start with a capable foundation model. DeepSeek V3, for example, is huge and has 671 billion parameters. Do a supervised fine-tuning step on a good quality reasoning dataset generated perhaps by another reasoning model. Use rule-based reinforcement learning to further improve reasoning. Perform a second supervised fine-tuning stage with a much larger dataset, this time including also general-purpose tasks data and not just reasoning examples. Conclude with a final reinforcement learning phase, which includes both rule-based and human preference rewards. So far, we've seen how inference-time scaling, pure reinforcement learning, and a combination of supervised fine-tuning and reinforcement learning can be used to build reasoning models. The last approach we'll look at builds on all of these ideas, and it's called Distillation. At 671 billion parameters, R1 is massive and expensive to run. This led DeepSeek to investigate whether they could transfer some of R1's capabilities into smaller, more efficient models through some form of distillation. Traditionally, knowledge distillation in machine learning involves training a smaller student model to imitate a larger teacher model by learning from the teacher's outputs. However, DeepSeek's approach was a bit different and quite straightforward. They took smaller LLMs like Llama and Qwen and simply fine-tuned them using the same 800,000 sample supervised fine-tuning dataset that they had used for DeepSeek R1. no further reinforcement learning was performed on these models. While the distilled models are not as powerful as DeepSeek R1, they still outperform the much larger DeepSeek R1 Zero and achieve solid performance on some benchmarks despite being much smaller. For instance, the distilled Qwen 7b surpassed GPT-4o on multiple benchmarks, and the distilled 14 billion model outperformed the Qwen 32 billion preview across the board. Additionally, the distilled 32 billion and 70 billion models outperformed even OpenAI's O1 Mini on most benchmarks. This finding reinforces that distillation can be an effective way to create cost-efficient reasoning models when combined with high-quality instruction datasets. Okay, if you're still with me, congratulations, you made it to the end. It's now time to wrap things up. Reasoning models aren't a revolutionary new type of AI. They are still next token predictors, just like any other LLM. What sets them apart is their training process, particularly the use of reinforcement learning tailored for reasoning tasks. Unlike standard reinforcement learning from human feedback, reasoning models use rule-based reinforcement learning for domains like math and coding, and this helps them develop structured and effective chains of thought. Larger models have an advantage because they can better retain and refine these reasoning patterns, but as we've seen, these capabilities can also be distilled into smaller models through supervised fine-tuning on high-quality reasoning datasets. This means that while size matters, smart training strategies can allow even smaller models to perform reasonably well on complex reasoning tasks. To conclude, I think it's useful to remember that the limitations we covered in a previous episode, and that are linked in the description below, still apply even to reasoning models. I like how Jeremy Howard summarized this idea in a recent tweet, referencing the paper Faith and Fate, Transformers as Fuzzy Pattern Matches. LLMs are fundamentally interpolators, not extrapolators. This doesn't mean that O1 and other reasoning models are just hype. Interpolation in high-dimensional spaces is incredibly powerful. I personally use LLMs every day, and I found O1 to be an improvement, especially for coding. However, exaggerated claims that these models exhibit human-like PhD-level reasoning miss the mark. Their strength lies in reproducing and refining known reasoning patterns rather than truly extrapolating new knowledge or synthesizing insights beyond their training data. If you found today's episode helpful, like, subscribe, and comment below. Let me know what topics you'd like to see in future episodes.